All right, college prep physicists, we're going to talk for a minute about momentum. Momentum is a huge concept in physics. And momentum is what Isaac Newton called a quantity of motion. So much like kinetic energy, momentum is associated with moving. And kinetic energy was 1/2 mass times velocity squared, and it was the amount of work you'd have to do to get something moving. Well, Isaac Newton was playing around with momentum without actually knowing it when he was doing his laws of motion, and he basically said that a force acting on an object causes an acceleration. But he also talked about the fact that it caused a change in a quantity of motion. So when you exerted a force on something, the quality and quantity of motion that that thing had would change. And folks figured out that quantity of motion, was another conserved quantity. So it has to be kept constant. And so they called it momentum. Now, I'm not sure why the symbol for momentum is lowercase p, but it is. And this quantity of motion is just mass times velocity. Now, unlike kinetic energy, that is a scalar, that is, say you square the velocity and you ignore the direction, momentum is still a vector. So I'm going to put an arrow over the top. Mass is not a vector, but velocity is a vector. So momentum is a vector. It has a direction. That means you have to be careful with the sign if you're dealing in one dimension, and you have to use vector rules if you're dealing in 2 and 3 dimensions. But the direction of momentum is the same as the direction of velocity. So it's not hard to find the direction of the momentum. And it's just mass times velocity. Now, these two recipes, they both have the same ingredients, mass and velocity, but they're of relatively different importance. Mass and velocity are equal partners in momentum. Mass and velocity are not equal in kinetic energy. The velocity is squared. So something that's moving fast has much more kinetic energy than something that's moving slowly. But something that's moving fast has a proportionally larger amount of momentum than something that's moving slowly. So there is a slight difference to these things. I could tell a story, but um, basically, in firearms, the caliber of your bullet often determines the mass of the bullet, and the heavier bullets tend to come out of the rifles a little more slowly than the lighter ones. But uh, so when we put together the M16 rifle for our army back in the whatever late 50s, 60s, it was a much smaller cartridge, a smaller caliber than the previous rifles used in, say, Korea or World War II. And the bullets would come out much faster. Now, to the Army, they thought that's great because if the bullets come out much faster, they have a flatter trajectory. In other words, the bullet tends to go where you aim and not fall down below that. Also, the ammo is lighter, but people discovered that when that bullet hit the target, the kinetic energy wasn't the important part, and the flatness of the trajectory wasn't the important part, that it was momentum that determined what kind of damage would be done at the end of the bullet's flight. And so our soldiers in Vietnam were finding that, hey, this rifle, I can carry a lot of ammunition and it's comfortable and easy to shoot, but I'm having to shoot people multiple times to have the same effect, or we're not penetrating through doors and trees and stuff the way we would with the older rifles. So that was a trade-off, and I suspect that the Army is going to go back to a slightly larger cartridge very soon. But that's just because the world has changed. So this momentum is a quantity of motion. Now, some other words that are associated with momentum. Another word is impulse. An impulse is the amount of impact that happens. So this is the momentum that you have. But let's just say that you were to shoot a bullet with this momentum, then when it hits something, it's going to have an impact on that something, and we can calculate the impulse. Now, impulse, sometimes abbreviated with a J, and this is confusing because joules are J, so I'm not going to do that. I'm just going to write out the word impulse. In fact, I'm just going to cover that up. That didn't exist. The impulse is equal to the force times the amount of time that the force is acting. And what an impulse does is it causes a change in momentum. So if we write this time as a change in time, and we move this around, we could say that a change in momentum happens when a force acts for a certain amount of time. And this is called the impulse momentum theorem. Um, Impulse momentum theory, and you can remember it because this says AP if you treat the delta as if it's an A, and this side spells fat. So AP is fat. That's how we remember it in AP class. So if you see a change in momentum, that's because a force acted for a certain amount of time. This is actually Newton's second law hiding in plain sight. Newton's second law said that a force equals a mass times an acceleration. But what is acceleration? Well, acceleration is a change in your velocity divided by time. And if you bring the mass in here and multiply it times the velocity, that means that a force is a change in momentum divided by time. And that's really the same as the impulse momentum theorem. That's why they say that Isaac Newton was really saying this when he said his second law of motion. So if you see something changing its momentum, that means a force acted for a certain amount of time. Now, some of you guys might be thinking about this. You might have noticed that this looks a little bit like what happened when we had work and kinetic energy, that you could have a change in kinetic energy if you had a force acting for a certain distance. So momentum and kinetic energy are brothers. They have the same kind of recipe. They do the same kind of thing, but they're slightly different than each other. And these are both forces. One's acting for a certain amount of time and one's acting over a certain distance. And this is really a symbiotic relationship. And the point is that both momentum and energy have to be conserved. That is to say that if there isn't a force, then the change in kinetic energy is zero. That means kinetic energy stays the same. If there isn't a force, then momentum will stay the same. So momentum is conserved in the same way that kinetic energy can be conserved. Now, energy, yeah, I understand the problem because kinetic energy is not conserved by itself. It's conserved as part of a family with potential energy. I got that. That is an issue. But just in this sense of looking at motion, comparing kinetic energy to momentum, there is a relationship there. By the way, momentum is conserved. That means that in a closed system, the total momentum is constant. Now, this is the same words, same phraseology as we had for our conservation of energy law, except the word momentum replaces the word energy, but it kind of means something different. Conservation of energy meant that the total energy was all of the potential and all of the kinetic for a single object. In the case of momentum, there isn't potential and kinetic momentum, it's just momentum, but there might be multiple objects. So the total momentum is the momentum of all the objects added together. An additional concern with momentum is that momentum is a vector, and so it has to be conserved separately for the x and y directions. And the same kind of thing we did with projectile motion, where we treated the x and y directions separately, and that gave us additional equations so we could solve more difficult problems. Momentum is the same way. Momentum is almost always used when you're dealing with collisions. Whenever you see two things banging into each other, you just know that momentum is going to be your dog. And the reason for that is that momentum is conserved all the time in collisions, but kinetic energy is not always conserved in collisions. Let's think about a car crash for a second. In a car crash, the two cars look very different after the collision than they do before. They are crumpled, rumpled, dented, sometimes parts have fallen off. Those processes take energy. So the kinetic energy goes into transferring from one car to another, bang, but also into damaging the two cars. So unless you can keep track of all the work done in creating that damage, it's not going to look like kinetic energy was conserved. But momentum doesn't have various channels to go into. So momentum is always conserved. When we do collisions, we actually, hey, let me get a fresh piece of paper. When we do collisions, we actually characterize them in a couple different ways. There are two main families of collisions. There are elastic collisions. Elastic collisions take place in such a way that no energy is lost. It's really hard to do. Usually the things have to not touch each other, like if you had two repelling magnets come close to each other, or if we sent a satellite to go around a planet and pick up some speed from the planet, that's actually a collision, and it's a collision, mediated by gravity. This means that kinetic energy and momentum are conserved. In this case, elastic refers to the fact that they always bounce off each other in an elastic collision. The word elastic means no energy loss, but you can spot an elastic collision because things bounce off each other. However, every collision where things bounce off each other is not necessarily an elastic collision. In elastic collisions, um, some energy is going to be lost. You can spot these. You can't spot them by whether they bounce off. They might be bouncing off, but if there's some damage done during the collision, it's most likely an inelastic collision. And that means that momentum is conserved only. And there's a third kind called perfectly inelastic. And these are where the objects stick together. So if you ever see the objects stick together after a collision, then you know it's an inelastic collision and you can only conserve momentum. You can't use conservation of kinetic energy. That is because some energy went into the sticking together, the binding of the two objects. So we're going to do a whole bunch of collisions where things stick together because mathematically they're a little easier. Then we're going to do some inelastic collisions where things bounce off and we have to use conservation momentum. Then we're actually going to do a couple of examples of an elastic collision where we can solve for a whole lot more things. In that sense. Okay, so let's put some examples here. Inelastic collision is almost always a car crash because the objects are dented. Elastic collisions include things like bowling and billiards. Billiard balls are very, very hard, and that means that they aren't damaged when you have collisions. It's almost always an elastic collision. And then perfectly elastic things that stick together. I'll use as an example train cars. Because train cars have that coupling thing that comes together and locks together so the two cars become mated, married, or otherwise stuck together. So these are the kinds of collisions. And these are their categories. We talked about impulse being an impact characterized by a force and a time of the impact, and when an impulse happens, that will change your momentum. Other than that, momentum obeys the conservation law, where the total amount can't change. And then anytime you see a collision, your first tool you should get out of your tool bag in physics is momentum. You should also know that momentum is a lot like kinetic energy in that it is reliant on mass and velocity, but different because it is different reliance and that momentum is a vector. There you go. That's the information on momentum.